One is the hydrologic routing, and the other is distributed or hydraulic routing. So the one we are going to see is the hydrologic routing, and specifically we are going to see the reservoir routing. So this is the general continuity equation for the reservoir routing, and the procedure we use to do the reservoir routing. So the first step to do in level pool routing is to find an average inflow values, which is this one. Okay, you have to calculate your average inflows. The inflow data at the inlet into the reservoir should be available, should be gauge data, and then from that data, depending on the time steps, you can do the average. And then after the average calculations, and you can find the change in storage over time, and at time 2, depending on the average inflow data and the previous stored water. So the second step, you have to find the current time storage by using this equation. And then normally when you start the analysis at time t is equal to 0 or at time t is equal to 1, we assume this value will be equal to 0, and then after all the observation, the calculation can be done by using curves or by using iterations. And but the main computational purpose, or the main computational point, is by using this equation. And once you're done for at one point, and you have to go back to the first step again. So here is the data we have. Okay, this is the data we have, the inflow data at a reservoir entry, and this is the spillway characteristic. This one is our spillway characteristics, and the C is the Augie spillway coefficient, which is given to be 1.7, and L is the length of our spillway, which is given to be 60 meters. Okay, and the surface area of the reservoir, at the crest of the spillway is given to be 28,600 meter cube. Okay, this is a cubic meter, QMX. Okay, cubic meter, and yeah, this is our spillway equation. So to start with, the first calculation should be with the average inflow data. So we calculate the average inflow here. We calculate the average inflow in a meter cube per second from the existing one. So average inflow at time 0 is usually not available. We just jump them because we don't have the preceding time. So at this point, or at time 2 is equal to 2, the average inflow at this particular time is the current time inflow plus the preceding time inflow divided by 2. So which means this one is I at 2 plus I1 over 2 is average inflow. So you can do that for the whole column and up to the end. Then now you have to find the inflow discharge Q. Okay, the average inflow at this particular time, you can just say 0, or we can just jump this like this. And Q is in meter cube per second. Okay, the equation given here there will help us to calculate that. And but we have to find, we have L and we have C, but we have to have H. So after Q, we need to calculate storage. Okay, storage is we are going to calculate it in a meter cube. It is a function of area times H. Okay, this is going to be obtained in a meter cube. And then after we find the storage, we can calculate this value. Okay, we can calculate this value at time t. We can calculate the change in storage minus the outflows over 2. So which means this is S1 over delta t, or we can write delta t as dt minus 0.5 or q over 2, q1 over 2, or sorry, the q1 times 0.5. This is also in a meter cube. So in this case we need to have time delta t, so we'll see how to find time delta t later. So at this point this value plus this value will give you the storage or change in storage at time 2, so which means S2 by delta t plus 0.5 of Q2 can be calculated here, but still you need to have H, so H will be in meter. Okay, and now the last column is we call that it's cell target. That is the one that helps us to iterate the flow flow routing approach, and to find H which corresponds to a given change in storage value. So in this cell target what we do is we directly calculate this value from area and the discharge calculated here. So if we assume our H to be, or if we start with 0, then we can calculate Q at this point being this is CL, so here's our C, and it is a constant value, fix it with a $sign, and then times L, this is also a constant value, fix it with a $sign, and then times of H here raised to 3/2, which is raised to 1.5, we can say that. Okay, say enter, and then you only calculate at that time step for a moment. Now you can calculate the storage here, so you have area here, and you have the H here, so area times H will give you the storage in a meter cube. But if you want to add these two values, if you want to add this value, or if you want to add this value with this one, usually you need to convert it into meter cube per second first. So for H0 we can calculate our area, so we have to fix our area like this because it's a constant value, and at initial time this is equal to the S1, this one, divided by delta t, so we have to find delta t. Delta t should be given in seconds. Okay, so here is the delta t, is the time step 0 to 2, 2 to 4, and 4 to 6. So the time step for this one is 2 hours, but somewhere down here when you reach the time step 32, the change in delta, or the change in time will be converted to 6 hours, 4 hours. So we have to consider that, or we have to bear that in mind. And the delta t for now is 2 hours, which is 2 times 60 minutes times 60 seconds, which means 70 to 100 seconds. So this is in second. Okay, and now you can calculate that this is equal to storage at this particular time divided by the change in storage to convert it to time. So fix this is a constant value as we are going to use it throughout the column, minus 0.5 times the Q value here. Okay, the Q1, then here is your value, or is your data. And at this point the change in storage at time t is equal to 1 is usually considered to be 0. We just jump as this, and for this one we have to calculate the value, this value, by other method. So we do this, this is equal to the area, okay, keep it constant, and times this H value, which is storage now, because area at the times H will give you a volume, then divide this by time. Okay, now it is converted to a meter cube per second, and then plus, okay, we are calculating this one in another way. Okay, so plus Q over 2, this particular time we can calculate that. So it is 0 for now. So we have to assume another H value bigger than 0. So because as the height increases, the flood amount increases at top. So let's say it is 0.1. Then for 0.1 calculate the Q value. So this is the Q value, and at the same time calculate your storage value and then calculate this one too, and then calculate this one as this one equals the S1 over dt minus 0.5 Q1 at time 1 plus the average inflow at this particular time. So with that you will have your S2 dt plus 0.5 Q2, and then at this point also from the equation you have the calculated value. So this value should correspond to this one. So we have to use some iteration approach to change that. So in this case you can go to your data tab, and you have see what if analysis, and under what if we have a goal seek approach. So the goal is, or the target cell should be this one, okay, and the value, or this value, should be equal with this one because they represent the same condition. So 18.4, the value should be corrected to, or the value should be iterated to this one. So to change this one we have to iterate the h value, and so I will say by changing this value. So you say okay, it will iterate it and give you the value, equate this value with this one, and then at the same time giving you the h value. Then assume any other h value which is greater than this one, 0.5. Then calculate all these values for that condition, and then calculate this one too. And then now we have to balance this one with this. So what I can do is I go to what if again, goal seek, then the target cell is this one, and that should be set to 562.507, and by changing this value, so say okay. So here you go, you have your values, and then the next step you can say this again, 0.5, and you calculate these all series depending on the h value, and then you calculate this one too. Then you have to balance this two, and you can go to what if again, goal seek, and then put this value equal to 1816, which means to this value they should be equal 0.71, and by changing the h value, then you say okay, so here is your result, and push this to 0.75 for example, and then here is your values, and then you have to balance this one again. So go to what if, here is what you get as a cell target, and this is your value, which is 4143.966. then by changing this value, okay, now that is been going well. So do that throughout the time, okay, do that, do this procedure throughout your analysis, okay. So when you continue doing that, the value of the Q increases up to certain points and it starts to fall down. So you can assume like 2.0 here, and sorry, you can calculate this one, and look if it balances each other. So it says it's 278 42.96 98, and then the target cell should be to this one, and this is what you get. And again you can change this value to 2.25 for example. So you can calculate this one, and you can balance these two values to 0.308 8.20443 with this variation, and here is your result. And again you can have another value 3.5 for example. You can calculate this value, and then if goal seek, and I set the value to 19841 0.8417, and change these values. So here's your dibs, and again you can assume in some other edge, and seek. At this point the time goes from 32 to 36, so the delta time is going to change. So the new dt will be dt2. Okay, this is the first one, and dt2 will be times 4 times 3600 seconds. It is 4 hours, so we have to change those things. So even if you assume h is equal to 16, and then at this point there is no dt. At this we don't have dt. At this we have the dt, okay, dt1, so we have to change it to, this is j2, we have to change it to j3. Right, and in this case also we have dt. Okay, we don't have dt in this case here, but we have dt. We have to change this to also 3. Okay, that is what we have.